Welcome back. In the last part of this lecture, we highlighted that crude oil was still, in your era, one of the important raw materials that is used by the chemical and processing industries. That area of chemical processing that we call petrochemicals. Crude oil, of course, took over from coal during my era, and it was very, very, very valuable because it made sites a lot cleaner and a lot safer. There was no longer coal dust flying around everywhere. What I would like to do in this lecture is talk a little bit about oil refining. It's still a very important process that chemical engineers need to understand. The origins of oil refining date back long before I started my career, you may be surprised to hear, because the first oil production and the first oil refining started in Romania in 56. I mean 1856, not 1956. By the end of my career, the last refineries I remember working on up in the northeast of England were immense. They didn't resemble in any way, shape or form those archived documents that I'd seen out of Romania from the 1850s. Refineries are one of the world's largest users of precious metal catalysts, and we need to understand both the catalytic part of refining as well as the distillation part of refining. So I'd like to spend a little bit of time now illustrating some of the things that they do. So I'm going to put a diagram on my blackboard. I'm going to start with crude oil, and I'm going to treat a refinery as a black box and just look entirely what comes out of a refinery. So there's my refinery. My refinery products are incredibly widespread. Natural gas, sulfur, petrol, diesel, aircraft fuel, naphtha, which is a C8 to C10 mixture of hydrocarbons, fuel oil, asphalt and coke. An amazing amount of different products from the one raw material. Now the thing to note, of course, that a lot of these products, especially things like jet fuel and motor fuel and diesel, have very, very strict specifications on certain physical and chemical properties. Their density range, their viscosity range, their flash point range, how much energy they give off when they burn, their lubricity. And so one has to be able to meet these very strict specification targets when one has a raw material of immensely variable composition. So the modern day refinery, the refineries you see in your era, are incredibly flexible processing plants. If we take the lid off this black box, and I put a diagram on my blackboard now of this black box with the lid off, this is a block diagram of a refinery, we see very many different processes going on. We can separate these processes into three major types. The first thing that happens to crude oil when it gets to a refinery is that it's separated by distillation, and you will see lots of different types of distillation process. I'll talk about these in a little more detail in a minute. Once we've separated various boiling point ranges out from the crude oil, we need to be able to match them to the products that we need. And so there's a lot of chemical conversion that takes place. Catalytic processes. Virtually all the catalysts used in refineries tend to be precious metal catalysts or ceramic catalysts doped with precious metals. And they chop molecules, they branch molecules, and they put molecules together such that we can try and match what the refinery needs to make to whatever raw material that we have in. The final process that you see is when we take all these different products resulting from catalytic processes and blend them together to make a saleable raw material. So blending is also an immensely important part of a refinery. So distillation, catalysis and blending are the three operations that you will see typically in refineries. When you look visually at a refinery, you see very large pieces of process plant. I've pinned some photographs to my blackboard, it took me a while, of typical refineries that you might see in your era today. Lots of chimneys, lots of integrated process plant, and lots of storage. By very nature of all the processes that go on within a refining complex, these sites are classified as major hazard sites, and so safety of operation is the absolute paramount necessity. Otherwise, if things go wrong in a refinery, and sadly sometimes they do, catastrophe does tend to happen. So, what I'd like to do now is to talk a little bit about the first process set that we looked at, distillation-based processes. So distillation happens when you get a mixture of materials. You have a unit operation that we call a column. It's a long, tall thing. And what we do is we have this column with a temperature gradient across it. It's hot at the bottom and cold at the top. And various different parts of the mixture that we feed into it boil at the various temperatures that we see going up the column. So you'll get very low molecular weight species boiling at the cold part at the top of the column, and you will get higher molecular weight species boiling at the hotter part in the bottom of the column. Of course, we can also control boiling not just by temperature, but by pressure. First of all, separation is carried out at atmospheric pressure. That gives us, in the bottom of our column, a residue that is very high in molecular weight. And we would like to separate it further because a lot of the heavy oils have these high molecular weight residues that are, in many ways, not very valuable, but consist of a large part of the raw material. We need to convert that into something else. However, we can't separate those heavy residues, as we call them, any further with temperature because they burn and coke, and you turn your distillation column into a coal mine. And I'm not joking, in my career I saw people getting into distillation columns with pickaxes to try and get rid of all the coke that had formed when something had gone badly wrong. What we tend to do instead is manipulate pressure for these heavy residues, and we distill under vacuum, because then we can use low pressure and lower temperatures to separate out these heavy species, but to avoid coke formation. So separation is the first thing that you see happening in a refinery, and it's a very, very important step. So on my blackboard, I'm going to give you a sketch of what I'm going to call a process flow diagram. It is, in effect, the roadmap of a chemical plant, and engineers use process flow diagrams, abbreviated as a PFD, to learn how a chemical process works. So, for example, a very simple PFD for a distillation system would be I would take my crude oil and I would heat it. The symbols on this diagram represent heaters of various types, heat exchangers or fired heaters. Once my crude oil is hot, I place it in my distillation column, that long oblate shape that the heated crude oil goes into. Remember, it's hot at the bottom and cold at the top. And if you follow the line that goes right out of the top, you'll see this passes through a fin fan condenser. This is another heat exchanger that removes heat. It removes heat much like a car radiator removes heat. You have a great big area of heat exchange material and air blowing over it with a big fan. That will produce both liquids and gas, which are separated out in that pot that it directly follows that condenser. Liquids are sent back into the distillation column as something that we call reflux. So if we look in our distillation column, we always have gas going up and we always have liquid coming down, and we always have mass transfer between the gas and the liquid. Which way the mass transfer goes depends where in the distillation column we are. So in the bottom of the distillation column, we have mass transfer typically from the liquid into the gas, where all the lighter species, the lower molecular weight species in the liquid, are boiling off the heavy species and going into the gas phase. In the top of the column, we might find that any remaining heavy species condense out at low temperature, and so we have mass going from the gas phase into the liquid phase. Sometimes we will see that distillation columns can be very complex. They'll have other columns bolted onto the side of them. And these other columns are typically called strippers, because a stripping operation in chemical engineering is where we remove material from either a liquid or a gas. So, the first step in a refinery is atmospheric distillation, sometimes with steam stripping. What we then do is lower the pressure, and if we have a look at the next bit of the diagram I've put on the blackboard, again we put heat into the system. Our second vacuum column is our big diameter column there. The pressure is lowered. I haven't drawn the equipment on here that we use to lower that. We'll talk more about that in future courses. But again, this vacuum column is where we allow all the higher molecular weight species to separate at lower temperature. We'll talk about why it's very wide in a minute. if you look on a refinery, you'll see that the distillation columns typically are the big tall things. Here in this photograph I've pinned to my blackboard, in the background you can see two atmospheric columns. They're relatively narrow in diameter but very tall. And in the foreground you can see a big vacuum column. Vacuum columns are huge, 5 to 6 to 7 meters or more in diameter. Now they have a large diameter because of course as we drop pressure, gas density will also drop. So for a fixed volumetric flow rate of gas, if our density drops, our velocity increases. And if our velocity of gas going up a distillation column increases too much, remember we said we always had liquid coming down a distillation column, the gas blows the liquid out of the column. So we solve that problem by making the column nice and wide, which will drop the gas velocity. If we think about the relationship between volumetric flow, area and velocity, the larger the area for a fixed volumetric flow, the lower the velocity. And so vacuum columns are very wide to prevent what we call flooding. Flooding is a very bad thing in distillation. So, separation is one important process in a refinery. The second important process is catalysis. So we need to think about some of the catalytic processes that we see following separation processes. Now remember, oil seldom has all the products that are required to make the final end products by simple separation alone. What we need to do is to have chemical conversion processes to convert low value products that we separate out into desirable high value products. Typically, this can be achieved by what we term as cracking. Cracking is when we get a low value, high molecular weight alkane, for example, and chop that alkane into 1 or 2 or 3 or different lower molecular weight pieces. And so from a C20 or a C30, we can make 3 C10s. And those C10s might end up, for example, in jet fuel or in kerosene, rather than in asphalt that you lie on the road as a C30. Typically, we like to make lots of molecules with more double bonds and more branches because the various specifications on our refinery products tend to be met by unsaturated hydrocarbons or partially unsaturated hydrocarbons and branched hydrocarbons rather than linear hydrocarbons. And so we have isomerization processes to convert linear hydrocarbons into branched hydrocarbons. Another immensely important catalytic process is the removal of sulfur from sour crude oils. As we said before, if we have sulfur in a fuel and we burn the fuel, we form sulfur dioxide, which is an acid gas, causing acid rain and numerous environmental problems. And so desulphurisation is also a very, very important refinery process, which is carried out catalytically. I'd like to give you some examples now of flow sheets, process flow diagrams, of these catalytic processes. So on my blackboard, I've put up a very complicated diagram, and I urge you to study this in your own time. This is a process called fluid catalytic cracking, abbreviated as fluid cat cracking or FCC. This is one of the processes used to chop long hydrocarbons into short hydrocarbons. It starts with long hydrocarbons as our feedstock, which I've put in a box in red. Now follow the blobs as they come on the blackboard, and that shows you where this material goes. It gets pumped up into a great big what we call riser. In this riser we have now a gaseous hydrocarbon, and it's combined with a catalyst which is a solid. And this solid is being blown along this riser going upwards, hence the name of riser, and the gas mixes in with that solid. And so there we have our gas and our catalyst mixture rising up into our cracking reactor. Now, all the chemical reactions that need to happen to chop up hydrocarbons happen in this cracking reactor. The products from this cracking reactor is then sent on to separation, because we don't just have one chemical species going into the reactor. We have a whole family that correspond to a boiling point range that we might have boiled off in our vacuum column. So we therefore need to separate out the family of cracked products that result into their useful fractions, such as fuel oil or naphtha. Now, when this cracking reaction happens, the catalyst tends to get carbon deposits on it, something that we call coking. And so these carbon deposits happen at the active catalytic sites, which renders our catalyst useless. And the speed with which this happens in hydrocarbon cracking is very, very fast. Typically, after some reactions have happened, the catalyst is deactivated by coke. And so we need a way of continually regenerating this catalyst. So the yellow dots now represent spent catalyst being blown down some ductwork into a second reactor that is hotter than the first. This second reactor is being fed with compressed air, also heated up to about 700 degrees Celsius. And in this reactor, the carbon burns off our catalyst. It's a fluidized bed, so all the solids are suspended on a bed of air, very hot air, and all the carbon burns off the active catalytic sites. Once that catalyst has been reactivated by removing the carbon, it goes back into our riser and meets fresh raw material coming in, and then goes forward into our cracking reactor. And so we have this continuous cycle of catalytic reaction, coking, decoking, and a new catalytic reaction happening in two different catalyst containing vessels. The off products from the regeneration reaction are typically gases, dusty gases. Dusty because in fluidized bed these catalyst particles start to hit each other and break apart. So we remove the dust, we recycle that dust where appropriate, and then we emit the clean gas up to atmosphere. So this is fluid catalytic cracking on paper. On a plant, it might look like the photograph I've pinned to my blackboard. Catalytic cracking processes are huge. The scale bar I've put is 12 meters. And so we can see that the catalytic reactor spans from ground level probably up to 40 or 50 meters high, maybe 8 meters in diameter. The regenerator, again, is up to 8 meters in diameter and maybe 20 meters high. So never forget in chemical engineering, when you see something on paper, a process flow diagram for example, never forget that its physical embodiment is a really serious piece of mechanical engineering, as I've illustrated to you. Now, let's talk about a second catalytic process. Let's talk about desulphurization. It's so important. And the example I want to give you is hydrodesulphurisation. It's another catalytic process, and we combine hydrogen with our sulfur-containing hydrocarbons. And the catalysis allows hydrogen sulfide to be produced, something that we call sour gas, and desulfurized hydrocarbons. And so our feed in this case would be sulfur-containing hydrocarbons. Again, I've circled my feed there with a red box. It gets pumped. It goes into some heat exchangers to vaporize it and make it from a liquid to a gas, and then goes into my catalytic reactor. This catalytic reactor is not a fluid bed, it's a fixed bed. And we see the vessel has a cross through it. That cross indicates a packed bed. Inside this packed bed, our gaseous hydrocarbon, our gaseous sulfur-containing hydrocarbon, meets hydrogen, and a reaction happens to produce hydrogen sulfide and sulfur-free hydrocarbons. The reactant products come out of our reactor. They give off their heat to help heat the incoming reactants, and are further cooled and further cooled and further cooled until the hydrocarbons that we have produced liquefy. And then the liquid hydrocarbons are separated from hydrogen sulfide in a simple vessel where the liquid collects in the bottom and the gases go up and out of the top. This is something that we call flash separation. The liquids, which are many in different chemical species, are sent for separation, and so we can distill out the various different chemical species that we desire. And the gases are then again sent for sulfide capture, something that we call amine scrubbing, such that we remove all those gases from any gas that we're going to emit to the atmosphere. And the hydrogen sulfide gas is then sent off for further processing elsewhere. Hydrogen sulfide gas can be very, very valuable because via a process called the Claus process, you can burn it and produce elemental sulfur, which is far easier to ship around, which you can then use, of course, to make things like sulfuric acid. So a few key points for you. I wanted to go through some of the very basics of refinery operation with you. Refineries are vast, complex plants that have a very tough job to do in terms of converting an incredibly variable raw material into very, very strictly defined products. Refineries have also been around since the 1850s, so they're one of the most long established pieces of chemical plant you will find. It is not uncommon for even modern day refineries in the US or Western Europe to have parts of plant that might date back 50 or 60 years. We've seen that refining has separation processes and catalysis processes. So separation processes, distillation primarily, takes place at atmospheric pressure and under vacuum. Catalytic processes are many and varied. They can be desulphurisation, they can be isomerisation, they can be cracking, just to name a few.